I'm Frank Cohen, and I'll be talking about non-abelian anyons. So generally, we think of bosons and fermions as integer spin and integer plus 1/2 spin particles, but due to the spin statistics theorem, we can equivalently think of them in terms of their exchange statistics, so the phase that they accumulate when we exchange two identical particles. It turns out that that's not the only possibility. We can also get what are known as abelian anyons. We can get any phase. But in the most general sense, we can get non-abelian anyons. And abelian is just a fancy word for commutative. As we know, multiplication by complex scalars is commutative, but multiplication by unitary matrices in general is not. And so that's where the term non-abelian anyon comes from. And these can be realized physically as quasi-particle excitations in 2 or fewer dimensions. Formally, that has to do with some algebraic topology, but heuristically, we can think about it as the fact that clockwise and counterclockwise rotations are not well defined in dimension greater than 2. So if we confine our quasi-particle excitations to just the x and y dimensions, then we need to make sure that we have ground state degeneracy in Z, and we want to make sure that there's no excitations from the ground state to the excited state in Z. And so if delta E is that characteristic energy gap, then we don't want any spurious excitations, particularly thermal fluctuations, similar to delta E, as is the case in superconductors. And so we can picture our anyons as these blue dots that are on these 2-dimensional sheets, and they're evolving in time. And as we know, fermions, their world lines cannot overlap. Bosons can in general, which is the whole idea behind Bose condensation. But it turns out that anyons cannot either. So those strands that you can see in green, red, and black, they cannot overlap one another. And so when we manipulate these anyons in time and we move them about one another, the path that they trace out cannot overlap. And that's related to the idea of clockwise and counterclockwise rotations. And that's significant because now the state of our system can be described topologically. And so with standard quantum computing, to date, all efforts for large-scale computers have been stymied by the negative effects of decoherence. But the promise of topological quantum computing is that decoherence will manifest itself as those little squiggles in our world lines, but that won't actually affect the topological state. And so in theory, our computations will be protected from the effects of decoherence. There's still some need for error correction because of thermal fluctuations greater than delta E, but this is hopefully a much less significant thing to worry about than decoherence with standard quantum computers. And so in this model of computation, we initialize our states by arranging anyons in some configuration, and then we do computation by braiding them about one another, and then we measure the state through what's called fusion. So for a quick timeline on the history of this field, in 1977, a couple Norwegian physicists first calculated that it might be possible in 1 or 2 spatial dimensions to get any phase, not just plus or minus 1. This was rediscovered in '82 by American Nobel laureate Frank Wilczek, who worked out more of the details mathematically. And that same year, the fractional quantum Hall effect was demonstrated experimentally, which we'll talk about later. And then a few years later, it was actually discovered that you could get not just abelian anyons in 1 or 2 dimensions, but non-abelian anyon exchange statistics as well. In 1989, Ed Witten introduced topological quantum field theory, which in our context is relevant because it describes the topological order of fractional quantum Hall effect states. And so this mathematically rigorous theory is kind of the framework upon which this field relies on, and he won a Fields Medal for that work. And then in '97, Alexei Kitaev, a physicist at Caltech, he proposed the idea of topological quantum computing. He took a surface code called a toric code, and he basically mapped the states of that error-correcting code onto eigenstates of a many-body Hamiltonian. And then a few years later, it was shown that topological quantum computers are universal, and in fact, they are equivalent. So they are no more powerful either than standard trapped quantum particle computers are. So in this model of computation, measurement is done by what's called fusion of anyons. And so fusion is basically the process by which we take two anyons and we bring them in close proximity to one another, and we see how they behave collectively. So concretely, if I had two fermions and I were to fuse them together, they would behave like a boson. And it turns out that the Hilbert space of our computation is defined not by the number of anyons that we have, but rather by the number of different fusion possibilities that we have within our system. And Abelian anyons always fuse into the same particle, be it a vacuum, fermion, boson, or another anyon. And that's why Abelian anyons cannot be used for computation, although they can be used for robust quantum memory. But it turns out that with non-Abelian anyons, we actually can get multiple different fusion channels for the fusion of the two same anyons. So here, n is a non-negative integer that describes the system degeneracy. So in general, there might be multiple physical mechanisms by which A and B can fuse to create C. And so as a concrete example, if we had the following fusion rule for A and B anyons, then we would actually get 6 dimensions in our Hilbert space from the fusion of these two particles. And gates are going to be implemented with what we call braids, so just manipulating the anyons around each other, and they will induce this phase, which is described by a unitary matrix. It needs to be done in the adiabatic regime. Basically, what that means is that we cannot perform these braids arbitrarily fast. But there's a couple concrete examples on the right where we see how you would implement single qubit gates, such as the Pauli X or the Hadamard gate, and the C0 gate, a 2-qubit gate, and you'll notice that we have 6 anyons for 2 qubits and 4 anyons for 1 qubit for the reasons described on the last slide. So now we're ready to talk about the physical implementation that we're pursuing to try to implement this model of computation. We're going to focus on fractional quantum Hall effect states. There's actually a few different routes that people are pursuing, hoping to implement non-Abelian anyons, including what are known as quantum spin liquids, such as frustrated magnets, and notably also Majorana zero modes. So to begin, the Hall effect, which we may or may not have heard of, if we have current going through a conductor and there is a magnetic field that is applied transverse to that current, then the magnetic field will apply a force on the charge carriers, and so we'll actually accumulate a voltage across the conductor, and this effect is most pronounced if we have a thin rectangular conductor, as seen in this picture here. And in 1975, a group of Japanese physicists predicted the existence of a quantum Hall effect, and this was realized experimentally by von Klitzing in 1980, who won a Nobel Prize for this work. But typically this is implemented in a 2-dimensional electron gas at the interface between a semiconductor and an insulator with high applied magnetic fields and very low temperatures, although recently we have actually implemented this in ambient temperatures with graphene. But in the equation on top, sigma is the conductance, 1 over the resistance, and nu is what we call a filling factor. And so in this case, nu is an integer. But we see the quantum Hall effect manifested in this data from von Klitzing's original paper, because as we vary the strength of the applied magnetic field, the conductance does not depend linearly anymore. It actually has these well-defined plateaus, which show that the conductance due to the Hall effect is quantized. And now finally, that takes us to the fractional quantum Hall effect, which was discovered in 1982. And notably, it cannot be explained by Landau theory. Landau theory has been extremely successful in describing phase transitions in terms of local order parameters. However, you can't describe a fractional quantum Hall effect state in terms of a local order parameter because it exhibits long-range order, which is why it is a topological phase of matter and why it lends itself to topological quantum computing. And so in this case, we see that the filling factor nu does not actually need to be any arbitrary integer. In fact, it can be any fraction. And two particular fractions that are of interest are 5/2, which we believe is going to be the easiest to experimentally demonstrate example of a non-Abelian Anyon, and 12/5, which is a non-Abelian Anyon that would actually give us universal computation. So 5/2 would not. It's called the Ising model. We would still need to implement some gates in a standard gate model without topological computation. But 12/5, if we could demonstrate that filling factor experimentally, that would allow for universal topological computation. So we would, in theory, be completely immune to the effects of decoherence, and that would really be the holy grail of this field. So to realize qubits using the fractional quantum Hall effect, we need to talk about the Aronoff-Bohm effect. So if you have an infinitely long solenoidal magnetic field B and some charged particle A, and you revolve the particle around the solenoidal field B, even though you're not directly interacting your particle with that magnetic field, it will accumulate a phase that is dependent upon how many loops it encloses around the solenoid. So that's a topological property. And Das Sarma proposed that you could implement a qubit using this effect because if you have current going, for example, from Q to N in the picture that's given there, it could either go directly from Q to N, or it could go from Q to B to A to P to Q to B to N, etc. There's a lot of different possibilities. And since this is a non-Abelian Anyon located at 1 and 2, as you revolve particles around it, you would expect that you would get interference and that you would be able to measure the effects of that interference. And the Willett group claimed in 2013 to have demonstrated non-Abelian statistics, but that claim has not really stood up. That paper has not been retracted, but to date, it is believed that nobody has actually demonstrated non-Abelian exchange statistics, in spite of the fact that we have demonstrated fractional quantum Hall effect states, because it's just very difficult to demonstrate this phenomena experimentally. So the success of this field in the future will really depend upon experimental verification of the existence of non-Abelian anyons, and hopefully in a way that's scalable. There are other ways to do it aside from fractional quantum Hall effects, as mentioned. Actually, in the past week, Microsoft has claimed to have demonstrated Majorana zero modes experimentally. However, as with the Willett paper and numerous other examples, we would probably be well advised to hesitate before we celebrate the arrival of non-Abelian anyons. And here are some citations. The two archive papers are the two papers by Kitaev, and the two resources there are really great introductory material. And here's the rest of my citations. Thank you very much.